All right, so we have some technical difficulties. So what happened is now student already discussed their approaches. So we're going to come back and then invite volunteers to discuss their case study approaches for the marriage rates in Italy. I was trying to say that what we got is marriage counts per 1,000 of the population from a particular 15 years of time. And the data is on Moodle. And then we asked every team or individual, if you team up or if you're working on it individually, trying to post your solutions to Moodle about your approaches. And we have this general question of marriage rates before, during, after World War II, the same. And then, of course, what are the Bayesian models, parameters, your MCMC estimation, and then lastly, your results. Okay. So we have all of the posts over here, so I can easily bring up anything that if anybody wants to get the discussion started of your approach and what is your conclusion and what kind of unanswered questions you might still have based on your analysis. So anyone wants to start? Either remote, I think we were able to hear everyone just now as well. So remote students, feel free to speak up and I can bring up your solution or anyone in the room. Yeah, Darlene, so.
You wanted to start by just looking at the data.
Yeah.
I was working with Leslie and Lewis.
Okay, so let me.
Our first step was just to make a scatter plot
Mm-hmm.
and we color coded. And so we did blue, purple, and then pink.
Mm-hmm.
Where blue is before, purple is during, and
Mm-hmm.
pink is afterwards.
Mm-hmm.
And just looking at it without running any formal analysis, we just looked and noticed that purple seemed to be lower.
Mm-hmm.
So that was kind of where we started.
Mm-hmm. And if now I go to your Bayesian model, can you talk a little bit more about the approach?
Yeah, since the data comprise counts,
Mm-hmm.
counts with Poisson distribution,
Mm-hmm.
and given that there was different means between the two options, I used the hierarchical model.
Mm-hmm.
So lambda j for each group. And so I wanted a question for you. That was how you said it's our hierarchical model.
Mm-hmm.
With the set of the density of lambda j and then lambda j. Like gamma distribution, hyperparameters.
Mm-hmm.
Also,
So alpha and beta, I guess both of them are positive, right? So is that the main reason why you chose gamma hyperprior for them? Okay, sounds good. So let's maybe pause here to take a look at the Jack script over here. Is the third member Louis? Do you want to talk about the code? Yeah, sure. I guess we get two loops over here. Let me zoom in a little bit more.
Yeah, so we were just trying to update with some of the code that we knew.
Mm-hmm.
And when we were updating our hyperparameters, right, because we didn't really have any estimates beforehand.
Mm-hmm.
We just kind of let alpha and beta be one.
Yeah.
Because we weren't really sure, I guess in our mind we had weak priors.
Mm-hmm.
So that's why we updated to that. We did up the fin a little bit, just because we noticed that there was a little bit of lag in, the modeling.
Mm-hmm.
So we decided to.
I see. So let me come down here. So I guess that's the fin update, right?
Right. Yeah.
Mm-hmm.
So we bumped that up to 5.
Yeah. So now let's look at. So was it before when you set up to be 1 and then you see some lags in the autocorrelation? Yeah. Keep going. Mm-hmm.
And that's pretty much how we.
Yeah. So then What will be the conclusion? Do you think they're different, the 3 different periods for the average rates?
Yeah, we said that there was, but we also like there was still some confusion about like what like how to really interpret our lambdas.
Mm-hmm.
Because when we do the summary, we get like lambdas, and then we have like the meaning for that.
Oh,
but,
I
like,
see.
Like we were still like a little bit confused as to like how we really interpret that in terms of like we see that they're different, but
Mm-hmm.
like what does that really mean in terms of like in terms of marriages and
Right, yeah. So I guess here, usually when you do the posterior summary, we'll be able to see, the mean, the median of each parameter, and they also very conveniently gives you the 95% credible interval in this case. Yeah, so any thoughts from others about, well, given, let's just say this output is what we get for lambda 1 for this row, lambda 2, and lambda 3. How are we able to compare or saying one of them, say, I guess earlier you're saying that the middle one is the lowest, right? Like from the data. So how can we further, I guess, based on this results to discuss whether lambda 2 is indeed quite different from lambda 1 and 3? Any thoughts? If we have output like this, or let's just say we have posterior draws, which I think is 5,000, right? I think from you all. So we have 5,000 posterior draws of lambda 1, lambda 2, and lambda 3. How can we evaluate the claim, like saying that lambda 2 is the lowest among the 3? How can we evaluate something like that? Yeah, Shinji?
I just want to take a guess.
Mhm.
I'm not that sure because at the very beginning, like when we kind of like explore the data, we kind of like had some saw like based on the meaning and the variance of all the data.
Mm-hmm.
So I'm thinking like maybe we can also calculate the mean value of like mean marriage rates before doing after World War II.
Mm-hmm.
So when we like after running Jack, maybe we can use MCMC function to kind of like get those 5,000 draws of lambdas 1, 2, 3.
Mm-hmm.
For example, like for data like 4, 2, then we can say maybe like use R Poisson like function in R to kind of like simulate 5,000 like simulations, and then like divide by 5,000 to kind of like see the mean.
I see.
And
I see.
compare the like posterior means.
Yeah.
That's all.
Yeah, okay, so let me just add to that quickly, and then Sarah will invite you to talk about it. So I think here lambda 1 and 2 and 3, we have 5,000 draws, posterior draws from the MCMC estimation. So if we directly compare them, which is similar actually to one of the take-home questions of the midterm 2, you could directly compare them and then return the posterior probability of, lambda 2 is smaller than lambda 1 and lambda 2 smaller than lambda 3 if you want. So if your focus is on the lambda, which is the parameter level. But what Shinji was suggesting is also, well, we could also generate predictions from the Poisson model that we know. And what that means is for each of the lambdas, we're gonna get, you could get 5,000, let's just say, predictions from our Poisson for the before, from lambda 1, for the during World War II, lambda 2, and then from after lambda 3, after World War II, which is lambda 3, and then compare the average, or I guess the mean of the predicted values instead of the lambdas themselves. Okay, so I think both approaches would be fine. I think it's really just depends on how you interpret the question. Are you talking about the average, if you think about lambda as the average mean, or I should say the average as the parameter, then you can directly compare the parameter level. But if you want to work at the prediction level, that'll be fine as well. Yeah, but I think either way, what we're gonna get is you will use R to, first of all, extract those parameters using as MCMC, I think from the CODA package. And then you'll be able to do manipulations either at the parameter level or at the prediction level. Yeah, Sarah?
Yeah, it's kind of like maybe this is what you are saying,
Mhm.
but so this is clarification.
Sure.
So we're getting lambda 1, 2, and 3
Mhm.
from the posterior,
Mm-hmm.
and we have like 5,000 of those, or like we have the mean of them.
Mhm.
Those 5,000 on the mean, we could whatever, we could put that back into the sampling model,
Mm-hmm.
which is the Poisson.
Mm-hmm.
But the mean of the Poisson model is lambda, so you can just compare them because you would expect that those, like the mean-ish of those sample draws would be.
Yeah, that's right. So that's why, yeah, so I think it's related. So I guess both will be fine, but then if you do 5,000 draws, most likely you will get very similar results even without doing the predictions. Okay. Yeah, so I agree. So I think either way, so I think it just like say, if we go back to the question itself, well, the question is asking, I guess, the merit rates before, during, and after World War II are the same or not. So if you focus on the average, then lambda is already the average, or which is the rate parameter of a Poisson distribution. So the posterior distribution that we're able to have over here, which shows you the mean here, here, and here, I think will just be, if you do a large enough number of repetitions of the predictions, I think the results will be very, very similar. Yeah. Would that make sense? Would that make sense for most people? Yeah. Mm-hmm. All right. Would this approach be what you did, or you have something else from other teams of the different approaches? Yes, Carl.
I just have a question because I saw what the other
Mhm.
talking about in the MCMC.
Do you know which one? Sorry. Oh, okay. Yeah, just go ahead then.
In the
Mhm.
MCMC, like when you say when you initialize the MCMC, I saw that team put the alpha and beta like values into the data with as well, and that is presumably like, because that would make the prior like hyperparameters not be used. I just wonder like what would happen to that, because I saw that the model still runs and there are still results. It's different from mine.
Okay. Yeah. All right. So I think what Carl was trying to say is here in the version that Leslie, Darlin, and Lewis had done, it is a hierarchical model in a sense that we put. Okay, let me come up here. Lambda J follows gamma, alpha and beta, and then each alpha and beta itself follow another gamma. Okay, so what Carl's question is, in one of those responses, he saw a version of it that kind of doesn't have anything beyond this part, but directly use 1 and 1 over here. And what does that mean? Okay, so let me repeat that question again. So this is one version of a hierarchical model, which I think is a proper hierarchical model for sure. Let me zoom in a little bit. Yeah. But another version, which some of you posted, is instead of giving a stage 2 prior altogether, like we don't give stage 2, we only have a stage 1, or yeah, like a single prior, doing this gamma, alpha, and beta. So instead of alpha and beta, they use 1 and 1 directly. Okay. And then of course, if I imagine what the MCMC iteration, like it will still be run, but I think for the output itself, at the very least, we won't see alpha and beta anymore, right? Because both of them are fixed as 1. So I think, well, I will just talk about what you're gonna see and then give you the chance to talk about what the implications. So like I said, in that particular case, alpha and beta are already considered as fixed as 1 in your model. So they're not parameters anymore. So what you will get, I think, probably in the posterior summary will just be about lambda 1, lambda 2, and lambda 3. Okay. And I guess, Carl, you're saying that you are the model still run, you still get results, and probably not very different from what we have, I don't know. But the question is, what is the difference between this model that we give further hyperprior for alpha and beta, and the other model that we don't have a stage 2 for lambda J, everything is only for the stage 1, which is the gamma 1, 1 prior. Okay, so that is a very good question. So let me pause here and give you the chance to think about what you think that really means in this setup. And how does that compare to, I mean, clearly those are two different models. Okay, we have the general beginning model, like the data model is all fine. We still have Yij, IID, Poisson. But this version has a two-stage prior for lambda j, whereas another version is only a single stage prior for lambda j. What's the difference and similarity between the two? Okay, so let me pause here and give you some chance to talk about it, and then we can look at it together. All right, let's invite some of you to share some thoughts. Well, like I said, those will be two different models.
Yeah.
Yeah, go ahead.
Is it still, are we still saying it's lambda J or are we just saying it's lambda now? That was.
Yeah, I think my understanding from Carl's comment is we still have lambda j,
Oh,
but then we have lambda j follows gamma 1 1. That's it. Like we end at the stage 1. And I'm sure it'll be wrong because it is still a proper model. But I guess the question now is how is it different from what we're doing right here? And which one, well, I guess now the question is which one should we be doing then if we really want to do a hierarchical model? Yeah, Sarah.
yes. I think with the hierarchical model, by having like the stage 2,
Mhm.
there's like a little bit more maybe like variability between the group, like the lambda, like the group specific lambdas,
Mm-hmm.
by kind of like skipping a step and just drawing from the same gamma 1 1 prior. You're having the assumption that I think that all the groups are maybe have like almost just, at least they're all distributed by the same gamma distribution. The variability that like the stage 2 would do.
Okay, so you think the stage 2 is introducing extra variability, or I guess uncertainty about what
Right. Or
lambda
especially if
j
you don't-
really follows?
Especially if you don't know how lambda j would directly be distributed.
Mhm.
If you could introduce it.
Right, yeah, so I guess, yeah, that's a good point. So gamma 1 1, if we give gamma 1 1 here, we kind of be sure that lambda j follows, each of the lambda j's follows the gamma 1 1, and kind of, well, that's the end. And then, all right, Brett?
Well, I was thinking about that. I think if the gamma 1 1 sort of looks like this, right?
Yeah, like this, yeah. Mhm.
So, which, and so that the averages you're getting are around like, or the rate, the variables you're getting are from like 5 to 9. Or
I think
something.
so, yeah. Mhm.
And that would, if you're taking gamma 1 1, most of your draws for the lambda would be around like from 0 to like 3.
Mm.
And so you would be drawing your like underlying rate parameter from a distribution that would be disproportionately giving, you would be ensuring that all of the data would be outliers. Sort of thing.
Right, so I guess, right, so gamma, alpha, beta, I think the mean is what? Alpha over beta, right? So if I use gamma 1 1, then the mean here in place of gamma, alpha and beta, and then further letting alpha and beta to follow their own gamma distribution, then the assumption that we're having here is a priori, we think each of the lambda j are going to be around 1 with certain uncertainty. I think the variance is also 1 because I think it should be alpha over beta squared. So that will be another issue, I guess, if we're directly using gamma 1 1, I guess, in addition to not having the flexibility of or letting lambda j to follow in a different gamma that we're not too sure about, which is what we can do in this version. And then at the same time, if we use gamma 1 1, then it might not be a very useful prior, or if the data set is too small, size is too small, then we might having a very strong prior in a sense that is deviating from what the data is telling us. Huh? Anything else? Yes, Junji?
I think maybe if you have like sufficient amount of data, then
Mhm.
maybe we don't need to set up multipliers because eventually like the prior like 5 by sequential operating will like become like.
Not very useful, or like not very having an impact, you mean?
No, I mean the like prior will eventually be what it really is. So, like,
Mhm.
posterior. But because like for this data set, like for each group, there are only like
Yep.
around 5 data points.
I think so, yeah.
We want to like add some like nuances. So because if you don't have like hyperpire for alpha beta, then I can think of it like as something like this, like the rate of update is kind of slow.
I see. Yeah, good point. Yeah, I mean, Shinji made a good point about the data size and then how that plays a role. So you see here, which is a nice summary that the team made earlier, is we get 4 and 6 and 6 different observations in the 3 different groups. So it's actually a very small sample. And that's why I think if, according to what Brett shared earlier, if we use gamma 1, over here, I think the prior will be very strong in a sense that the results, once again, if you ever want to fit it and just give it a try, the results compared to what we have over here might not be very close, simply because the data size or the sample size is kind of small, and then the prior will play a very strong role in the MCMC estimation. Okay. At the end of the day, I should mention that, well, this is kind of like the way that we did for the hierarchical model, for the normal model that we did in class. So really, when you have 2-stage prior in this particular way, that we can actually classify it as the hierarchical model in the first place. Okay, if you just do it as gamma 1, yes, you are allowing the lambda j to be related to each other, but it's not technically a hierarchical model in the sense that we usually talk about. So a 2-stage or even 3-stage, multi-stage prior setup, you can think of it as a key feature of doing hierarchical modeling in the first place. Yes, Sarah?
Question about like for like gamma.
Mhm. Mhm.
The alpha and beta.
Mhm.
Is gamma 1 always a good one to use, or is that only for the normal like gamma 1? Like, is it different when we are saying that like because it's not like we're distributing like I don't know if that makes sense.
Yeah, right. So so there are many further explorations people have done in terms of what kind of priors to give for certain parameters and all that. I think in class we've been saying that, well, if you have a positive quantity, then gamma, not necessarily gamma 1, but gamma something is not a bad choice, because it will give you strictly positive quantities. So I agree. So in terms of gamma 1 or gamma in general, I think it's definitely a conjugate prior that we usually use for the precision parameters. So for the normal example, so that's what we've been doing a lot. And I should also say many of the in-class midterm derivations that we have been doing, gamma seems to be a very popular choice, as you could imagine. So that's happening in practice as well, because gamma, not only for the precision parameter is conjugate, for Poisson model is conjugate, and for many other quantities in certain models, it's also conjugate. So you're able to get the full conditional posterior and all that. So it is a popular choice over there for that sense. But I should also say that given what we've been doing with JAGs, it's not necessarily it's going to be a gamma, right? As long as it's something positive, and then you can deal with it pretty easily, because we don't necessarily deal with the full conditional posterior distributions. JAG's going to pick the most efficient MCMC estimation. Yeah. So FYI, sometimes people like to give, say, positive t distribution for precision or standard deviation. So that means you're only looking at the positive side of the t distribution. And you have seen what we did with the truncation, right, in JAGs. So that can be set up pretty easily that way as well. So student t distribution is a popular choice for standard deviation. And maybe some of you have heard about the distribution called Cauchy distribution. So also it's similar, symmetric, similar to a normal in some sense, or a t to some in some sense, but then only picking the positive side. So that will be another popular choice as well. So for gamma 1, it's almost like what we've been talking about. It's like a default choice if you don't know much about where it's going to lie. I agree, it has mean 1 and standard deviation 1 as well, so it might not be the best choice in many of the applications. But nevertheless, I think most of the time is quite weakly informative. So if you don't know much about what you want to use, then this could be a good one to start. Yeah. Yeah, Carl?
I just have like a question about
Sure.
the mechanism of the hierarchy model in general.
Yeah.
In a case where we don't have hyperpowers,
Mhm.
essentially we're just, if we have like gamma 1,
Mhm.
or all ranges,
Mhm.
it's basically like estimating on like 3 separate data sets, right? It's like separate estimating individually.
Yeah,
So the
good point.
data would directly drive the posterior of lambda.
Yeah.
But in the case where we have hyperpowers,
Mhm.
the data are driving the posteriors of alpha and beta.
Mhm.
But would they still directly impact the draws of lambda then?
Yeah, good point. And I think Carl also made a good point about why we don't want to use gamma 1 over here, because if you do gamma 1 for this lambda j, then essentially you're treating all of the data points into 3 different groups and you're doing separate estimates. Okay. So even though you give the same prior for all of them, but it's given, you're not estimating, like nothing is being shared across the groups anymore. So if we go up to the table, so pretty much I have a gamma Poisson model for the first group. I have a gamma Poisson model for the second. I have a gamma Poisson model for the third, and then I'm done. Like I'm not really pulling information across the different groups, which is the key feature of doing hierarchical modeling. So that's a good point. And then the second point Carl was trying to make earlier as well, when we have this proper hierarchical model that we're doing over here, and then we will have posterior estimate of alpha and beta, and then the lambda j, which each of them going to follow a gamma, lambda, alpha and beta and all that. So the question is, the posterior of those hyperparameters, alpha, beta, how do they affect the lambda j, I guess, in the MCMC? Is that what you meant?
Yeah, no, like does the data still, because I know like
Mhm.
so gamma, alpha, and beta would be the prior
Mhm.
of lambda, but would the data play a role again in the estimation?
For each of the lambda j? Yeah, it will. So let me see. So if any of you took a look at one of the derivation that I posted, maybe most of you did when you're preparing for the exam. So this was the hierarchical normal model that we did, if you remember. So we have this is the K-drama example. So we have Yij, which is normal mu j, and then you have a bunch of, the hyperpriors and priors going on. So let me show you one thing. If I look at the joint posterior, let's see, the joint posterior distribution, if I look at a group mean, okay, if I only look at the posterior distribution of this, let's just take a quick look at what this equation 14 shows. Okay, I mean, the general format is still very similar to what we had done using the normal model just to do the derivation. But what I want to highlight over here is that if I'm looking at mu j only, then you can see that the update actually only depends on the Yij from the group J. And then similarly, the data size or the sample size of group J matters, but then any other group size doesn't matter in terms of, yeah. So if we do a derivation of this model, which I'm sure we could, because we're using a conjugate gamma over here. So you should be able to get a conjugate, or I should say full conditional posterior distribution for each of the lambda. But then the Yij that's going to contribute to that full conditional posterior distribution only comes from group J. And then that is how the data for a particular group is contributing to the group mean, for example. But then I'm sure your follow-up question will be, well, what is being really shared in that case? So if I look at 1 over sigma squared, you can see that all of the observations are contributing. Oh, sorry, down here. All of the observations are contributing. And the same for mu, which is the group, the overall mean for the hyperprior over there. And that comes from all of the mu j's that you're having. And I think similarly for tau as well. So I think the takeaway message is that when you're trying to do full conditional posterior derivation for this more complicated models, you will see that anything that is very specific to a group, if you're looking at the full conditional posterior distribution of it, it should only extract the data from that group, because that's only what matters for that update. But what's being shared is the alpha, is the lambda, and earlier for the normal, it's the mu, is the tau, and the sigma. And those are being shared because their full conditional posterior distributions are having contribution of all of the groups together. Yeah. So that I think is an indirect way to also say that, well, if this is one, this is also one, nothing is really being shared anymore. And just like what Carl, you pointed out earlier, that is equivalent to fitting 3 separate models off together. I'm not letting anything to share across the groups. Make sense? Okay. Yeah, Shinji?
Like, I have like a question.
Sure.
related to that. So basically, like when we first learned the hierarchical model, like in class, we kind of like talk about normal distribution, like it's kind of like a data model. And then like we talk about like the 2 parameters. So mu is like group specific, but we don't we didn't say like sigma as group specific because we want to kind of see the kind of like the relations among like all the data.
Yeah.
But in this case, it only has like 1 parameter.
Yeah.
And you're saying that like by setting up like hyperparameters, we were still like getting the, like kind of like the overall effect. So let's go back to the normal distribution. So why don't we set sigma as like group specific parameter as well?
Yeah, we were trying to do it, but okay, so this is I guess flashback of what we're trying to do. So because for the hierarchical modeling example that we did in class, in fact, if we look at the data, if you remember, it is actually suggesting that we should use group specific mean and group specific standard deviation as well, because what the data is telling us. So I think that's the better model to use for sure. The reason why we didn't do it in class is because that will add up the complexity of the model. So we didn't do the one for sigma j, but we also, well, maybe you don't remember, but we did a short discussion about what you could do if you want to have group specific mu j and sigma j as well. And that's what we did for, expanding this lower part into further of, sigma j contributing to each group. And then you can have a shared prior for sigma over there, for example, another gamma or something for that. So I think it could be done, and it should be done because of how the K-drama data set is like. We didn't do it for the simplicity of introducing hierarchical model in the first place. But if you're curious, like the derivation that I showed earlier, of course, if you now start to add a sigma j over here, the whole likelihood will be updated. You won't be able to write them down, or like you have to have a sigma j over here as well. And then the posterior, full conditional posterior for each of this right now will be a very specific to sigma j. And then all of this will have certain updates as well, because you will only, just like following the logic earlier, to update sigma j or 1 over sigma j squared, most likely you're only going to use the data from group j.
So for hierarchical model, like for group effects, like group effects kind of like presented by the group specific parameter in the original data model.
Yeah.
But like the overall effect is like kind of demonstrated by the
hyperparameters.
Okay.
Yeah, exactly. Yeah, so I think going back to the discussion earlier about all of this as well, it is this alpha and beta being shared across the group, okay? Because the update, if you try to do the derivation, the update for the lambda j, I think will only grab a yij that j equals to the particular group that you're doing. But then what is being shared is all of the, at the lower level is all of the hyperparameters, which is also probably manifested by the hierarchical structure that we did. This one. So if you look at this, mu1 only contributes, right, to yi1, like the first group. Mu j only contributes to the jth group. So, and actually from this graph, I think another way to think about it is, well, the sigma, the mu and tau, they are being shared across all of the groups. You're still going to have group specific mu1 and mu j, and later if you want to do sigma j, you're going to have group specific as well. But then their hyperparameters are what being shared across all of the groups at the I guess, yeah, the lower level in terms of when you're trying to think about the relationships. Okay, Anything else? Is this approach pretty much how everybody did it? The hierarchical gamma Poisson, kind of? Sounds good. Yeah, so I think that's definitely a good choice in this particular case. And again, the data set is not very complicated, but because of that, also the sample size is really small. We really wanted to make sure that we use a weakly informative prior, because otherwise we're driving the inference too much using the prior that you use, unless you have very strong belief about what they should be. Otherwise, I think it is useful to use weakly informative prior. And then, of course, make sure to do MC diagnostics for every parameters in the model. And then you can adjust your thinning, or sometimes maybe burn in as well sample process to make sure that your MC has been mixing well. And then based on the final ones, you can come up with your conclusions and all that. Okay. Okay. All right, good. So with that, I'm gonna stop share. And like I said, the rest of today's lecture we'll have about 20 minutes left, so you can work on your project. Happy to answer questions. And I will also give back the midterm too as well. I think everybody did well, even though I know it's challenging, but overall it was good. So I posted the take-home part on Moodle already, so you should be able to see your scores and also the graded over there. And the average, I think, for the take-home part is 18.3 out of 20. Okay. And the in-class version, which I'm returning right now, but the grades are also on Moodle. Out of 30, I think the average is 26.5. Okay. That's it. So let me stop recording on my end over here. But Nathaniel, Noah, feel free to stay to ask any kind of questions you have about projects or other work that you're doing. I'm just going to try to stop recording.